Welcome to our latest Explainer. Today, we're going to unravel a massive geographical mystery. Exactly where humans live, and more importantly, why. Have you ever wondered why some parts of the world are absolutely bursting with life, while others are just completely desolate? Well, we are taking you from a view in outer space, right down to the soil, to decode what we call the crowding paradox. Let's get into it.
Okay, if you picture our planet glowing in the dark from space, you'll instantly see that human settlement isn't just some random scattering of dots. It's actually incredibly specific. Bright clusters bloom over places like Western Europe, the Eastern US, the Ganges Plain, and Japan. But then you have these vast stretches of land, like the Sahara, the Siberian taiga, the Amazon basin that are just pitch black. That luminous map tells a story demographers have documented for centuries. Humanity has always packed itself into a tiny fraction of the planet's surface.
And that glowing map brilliantly illustrates our first major clue. Get this, an overwhelming 90% of the world's population is squeezed into roughly 10% of the total land area. It's wild to think about. Most of us are clustered right in the middle latitudes of the Northern Hemisphere. Understanding exactly why we cluster so tightly together is literally the starting point for all of human geography.
Now, geographers actually have a specific name for this inhabited zone. They call it the Ecomin. Historically, this zone perfectly follows regions with reliable rain, fertile soils, and access to trade routes or navigable water. It's the permanently inhabited portion of the Earth. But it's important to remember that the boundary of the Ecomin isn't completely fixed. Land that was once totally empty, like the Arabian Desert before oil-funded desalination, or the North American Great Plains before steam-powered agriculture, can actually get pulled into the Ecomin as our technology evolves.
On the flip side of that is the non-ecumen. These are the extreme environments that actively push back against human settlement. We're talking high-altitude zones like the Upper Andes, the extreme dryness of the Atacama, or the freezing tundra of northern Canada and Siberia. Together, these incredibly harsh regions cover roughly 60% of Earth's land surface, but because of the extreme cold, the steep terrain, or just a total lack of water, they support less than 5% of our global population.
So, knowing where people are is really just the starting line. The true mystery is figuring out how we measure them. And that brings us to a really crucial question. How crowded is too crowded? It sounds simple, right? But the way we traditionally measure population density can actually be incredibly deceiving.
Because honestly, saying a country is densely populated kind of conceals way more than it reveals. A single country might have a massive, bustling river delta, but right next door, it could have completely empty highland steppes. So to truly understand crowding, we need a specific diagnostic toolkit made up of 3 distinct measures.
Let's look at our first tool and see how this builds. Arithmetic density is the absolute simplest and most widely cited measure out there. You just take the total population, divide it by the total land area, and boom, it tells you how crowded a country looks on a map. But as you can probably guess, it can be super deceiving because it treats all land as equally available for settlement, which, as we just saw with the non-Eucomane, is almost never true.
So, to get a much more accurate X-ray of a nation's real food security, we use our second tool, physiological density. This is the total population divided only by the area of arable or farmable land. Because not all land can grow crops, physiological density reveals the intense, real-world pressure being placed purely on the land that actually produces food. A country with a high physiological density is placing massive demands on its cultivable soil.
Finally, we have agricultural density. This tool measures the number of actual farmers divided by the area of arable land. And what this really measures is the technological intensity of the farming itself. A really low agricultural density means highly mechanized farming, so just a few farmers using advanced tech to farm huge areas. A high number, though, means the country is highly dependent on manual human labor just to get crops out of the ground.
All right, let's put this toolkit to the test and look at the density paradox in Egypt. On paper, Egypt has an arithmetic density of about 104 people per square kilometer. Crowded, sure, but hardly alarming on a global scale. But here's the catch. Only about 3 to 5% of Egypt's territory is actually cultivable. When you restrict the math to just that arable land, Egypt's physiological density explodes to nearly 3,000 people per square kilometer. In reality, almost everyone there has to survive off a tiny ribbon of the cultivable Nile floodplain, which is completely surrounded by lifeless desert.
This gets even more fascinating when we compare extremes. Let's look at the Netherlands alongside Egypt. The Netherlands looks way more crowded arithmetically, with a staggering 510 people per square kilometer. But check out their agricultural density, fewer than 3 farmers per square kilometer. Because of extreme technological automation, capital-intensive methods, and greenhouse farming, a single Dutch farm operator can produce more food than 50 smallholders somewhere else. They have literally solved their land pressure problem through pure technology.
The 4 great human hotspots, where the majority of the global population is anchored.
Zooming back out from our specific case studies, we find that over half of all living humans are anchored in just 2 of these hotspots: South Asia, with nearly 2 billion people, and East Asia, holding roughly 1.6 billion. Historically, these incredibly dense clusters have been driven by highly fertile river valleys. Think the Ganges, the Yangtze, the Yangtze, paired with intensive wet rice cultivation that supported massive populations for thousands of years.
But notice how the logic behind the crowding actually shifts depending on the region. While the massive Asian clusters are deeply tied to agricultural capacity and those fertile plains, the European cluster and the huge megalopolis stretching across the northeast US and southern Canada follow a totally different logic. They're packed tightly together, not because of farming, but because of modern industrial, urban, and commercial development. It's a completely different driver.
Now, if you're analyzing these clusters yourself on a choropleth map, the ones that use different colors or shading to represent density, you really need to follow 3 essential steps. First, check the class break intervals, because different math reveals totally different patterns. Second, analyze the pattern at multiple scales. And third, always identify what the map cannot show. A single arithmetic density value for a whole country simply cannot distinguish a booming, packed city from a completely empty rural hinterland. Figuring out your unit of analysis prevents that common trap of treating political boundary data as if people were spread evenly like peanut butter across a whole territory.
All of this mapping, measuring, and analyzing naturally brings us to the ultimate limit, which is carrying capacity. Think of this as the theoretical ecological ceiling of a landscape. It's the maximum number of people an environment can feed, water, and shelter indefinitely without permanently destroying the underlying resource base.
But here is the absolute most fascinating twist, and it's something you definitely need to take away from this explainer. Carrying capacity is not a fixed biological constant. It's not set in stone. History proves over and over that human ingenuity can completely decouple food production from local land area. Ancient Rome used to regularly feed a city of 1 million people using grain shipments from North Africa. And today, the Green Revolution and Dutch precision agriculture prove that technology, trade, and social organization can actually push that ceiling higher and higher.
And this exact point sparks one of the most intense foundational debates in all of human geography. It was famously championed by the Danish economist Esther Bosserup. She argued that population growth isn't just some burden that bumps up against a fixed ecological ceiling. Instead, she proposed that population pressure is actually the very engine that drives societies to innovate. It forces the technological and social changes we need to raise the carrying capacity itself.
So, I'm going to leave you with this final provocative thought to ponder today. As our global population continues to shift, to concentrate, and to grow within these dense human hotspots, are we inevitably going to crash into an unyielding ecological ceiling, like some fear? Or, as Bosserup suggests, will the intense pressure of all those people packed together force us to build an entirely new, higher roof? Think about that the next time you look at a glowing map of the world at night. Thanks for joining me on this explainer, and keep questioning the world around you.